Welcome back to High Performance Computing, our lecture 6, the second part of it, an introduction to deep learning. So in the first part of deep learning, actually in this lecture, what we really tackled was not really deep learning, it was machine learning. And the idea is that basically many of the aspects of deep learning are derived from machine learning. So you will find that the perceptron linear learning model that I showed you in the first part of the lecture captures the essence of a so-called neuron, which is a little bit modeled like the human brain, missing some aspects, but the very simple learning model, linear learning model, linear in weights. You have seen we give the input signal and then we sum them up linearly using weights. We had an activation function that is going through it, which could be the rectified linear unit. And then if you add more hidden layers and combining the power of one of this neuron, right? And this is now a very important term because that's where the neural network obviously comes from, that you form a network of them. And in that sense, what you can do with this is what actually the XOR example nicely showed, that with one neuron, you cannot go very far. You have a linear decision boundary. You basically have a linear learning model, so you cannot learn so-called non-linearities. In other words, the linear decision boundary that you learned, remember Iris setosa, Iris veronica, the different flowers in part 1. This is basically unachievable if you don't have a linear separable data. So what you basically was seen was a really idealized scenario in the beginning of this part. I mean, basically in part 1 of this lecture. So this is happening rarely in practice that the data is linearly separable, as we would say it. Hence, the idea is, of course, having more non-linear decision boundaries. And the way to do so is not only to have, of course, now an activation function that actually activates so-called non-linear activities. One of it is that the rectified linear unit is basically, 0 in negative, but positive, increasing in the positive space. So, and I have basically have given you some examples of the punch and so on. That also gives me the maybe opportunity to say, of course, this is a HPC course, right? So if you want to really learn about deep learning, you have to either do one of my trainings 3 days or maybe even a whole week that I did in the past here and there. And, it's some of them are in YouTube, but also the centers, the centers, when I refer to this, usually stands for supercomputing centers, Barcelona, Finland, CSC. You have also, of course, Jülich, the center we are affiliated with, but many of the centers have also many trainings they offer. And then we do deep learning for 5 days or 3 days even. And the 3 days course might be even, having a prerequisite in my past to have machine learning basics first. So I have another 3 days course where we learn machine learning basics in the past. Hence, long story short, if you're really interested in these subjects, you have to learn. And I would basically refer you to my colleagues here at the university to do a proper machine learning course, right? So there are lots of different elements that in the first course part of this particular lecture we already skipped. And 2 of them I wanted to really note highly because this captures the essence from a, let's say, beginner of machine learning to an expert. The first is regularization and the second is validation. So these topics, 2 of them you have to master. So regularization usually combats overfitting. You penalize the learning a little bit because you don't want to really learn every single detail of the data. You want to learn the pattern that is behind this data, right? So in some respect, every single data doesn't really matter. You want to go through all the data, learn from it, but you want to basically then be ready for unseen data, what captures the essence of machine learning. I know that's sometimes hard to understand for some of you that basically have not a machine learning course yet, but we want to basically have a learning model or a deep learning model, a machine learning model that actually learns from existing data and then performs very well out of sample, right? So what we learn is in sample. That's where we learn from. what we learn for is out of sample things we don't know, the future, some unknown data item, data point, whatever, classification of something unknown. And this is something where we call that out of sample performance. And this is something what matters a lot. And again and again, I would say this is something where regularization comes quickly in order to do performance like improvements in terms of dropout. You so here and there remove some of the neural network weights for purpose, or even if you don't do it so strict, you can actually penalize the learning also by so-called weight decay. And there are many others, early stopping, another regularization technique. So basically, again, a proper link to a machine learning course, but here, of course, in the HPC, the more important takeaway message in the first part of the lecture was the increase of the trainable parameters, right? If the more capacity we have in the learning in the model, from simple learning model with perceptron up to artificial neural network, we have quite seen an increase in, going from 8,000 trainable parameters to 120,000 trainable parameters. And you pay the price for it. All of that is basically done by update the gradients, go through by propagation, update the waves, and the optimization step, of course, takes some time to do. Now, before I go into the material lecture part 2, I also want to highlight validation, because this is the second part, right? I said regularization and validation captures the essence from a machine learning, let's say, beginner to an expert. So validation stands largely for model selection. And this is a huge course. So normally in a machine learning course, I would spend at least 2 lectures on it. And validation means many different things in terms of practicality. So if you swim in data, you would put a validation set, or maybe 1 or 2 or 3 of them. Usually it's not like that. So we employ techniques called cross-validation, to reuse data again and again. And the key reason is that when you pick a certain model in machine learning, right, let it be the CNN we do now, or the artificial neural network with 2 layers you have seen the last time, or we add 2 layers 4 times, 6 times. This is not maybe useful, but still, if you do it, it's your human bias you put into the learning process. So we call that so-called an optimistic bias. And in the end, it's in this data set. So you take, let's say, an input in the learning progress, and that's not good in a sense. So we put a bias in, and in this sense, the validation data set, hence the connection to model selection. It's your model selection, your number of parameter set you choose. Is it 2 hidden layers, 4 hidden layers? Is it 128 neurons in the layer 1, or is it 300 layers? Neurons in 1 layer. So all of these decisions, the learning rate, this is a hyperparameter, yes, but still, this is, you take advantage of a model selection in terms of how the model look like itself, a parameter, which basically is then something where there are some real problems. Hence, a validation set would be contaminated if you take this decision and you throw it in the corner and never use again. And then you would use a test set, right? After training, the validation performs, and then you use a test set to really report to your bank or to Netflix, wherever you get the check from for your machine learning problem you implement, and then actually get some credit for it or money. You would report it on the test set. But again, basically the important is also to first never touch the test set for learning, right? So it should be hidden in the corner, throw it in the corner, never seen again before you actually test. So never train on the test set and then use the test set again for, evaluation of performance. And in proper machine learning courses, they should teach you about validation sets, which are usually done before we do basically getting ever to the test set in order to perform then the final model selection. So here today, in the second part of the course, I sort of do in bias automatically by introducing you to the convolutional neural network. So this is material of deep learning. So that wasn't existing many years ago, or in other words, it was existing ideas, but we never had the computational capacity. And now that's the point to the course. right? So deep learning is largely enabled by high performance computing, by the evolution of GPUs we have seen. And you also feel that quite literally if you actually train on this particular data sets with this particular networks. So let's dive into the material finally of this lecture to understand what I mean and also to understand the connection then to the trainable parameters. Obvious to say, the lecture is called Introduction to Deep Learning, and I could now talk a whole lecture course about it, right? So this is not something you can capture in any way in one lecture, if you be honest. So these days we see tremendous impact of deep learning, and this is just an overview of some areas of applications where deep learning has made a big difference in vision, natural speech, natural language processing. Deep learning is by far, you have heard about large language models. This is by far the modus operandi. So nobody goes back in time and thinks what we did in 20 years ago. There's other, even non so obvious pathways where you would say omics, right? You have heard about AlphaFold. You have heard about different protein folding ideas in the past, and maybe now AlphaFold is there, and suddenly we have interesting breakthroughs. Even in the domain of fluid gas dynamics, and this is really interesting because this is a domain driven by physics. I'm referring more to the lower part because I think the medical imaging diagnostic is very obvious. It's image recognition, where neural networks are very similar, like the vision upstairs, or basically have seen significant breakthroughs. Now, the interesting thing is like in fluid gas dynamics, things which are really driven by, you would say, numerical methods, right? Driven on physical laws, implementing physical laws. This has been changed significantly in the last 10 years. Hence, we have AI factories in Europe. We have soon maybe AI gigafactories in Europe. We have a tremendous momentum around AI because it shapes the field suddenly enormously. Also, of course, just to refer quickly to it, AlphaGo, I think you heard about this, that this was a game that never was basically possible for some computer to learn because it's so complicated. But there was of course, AlphaGo that then actually led in the evolution to AlphaFold for protein folder and so on, also beating a human in this game. And you can go on and go on, and I could talk hours about this. My whole research field based on transformers, based on autoencoders, remote sensing with some of my colleagues from electrical engineering. So we do lots of this with HPC and deep learning. And by now, I think no matter what you hear from others, deep learning cannot be just talked away. So it has a standing, it has significant breakthroughs, publications, and many benefits in terms of, let's say, also what we call more or less getting the out of sample right. And also with the tremendous idea of computing now, we can go ever bigger. And the slide here you have seen before, I just want to remind you again, in one respect that, of course, the tremendous success we have is not just AI people were very smart and say, okay, we have this now deep learning networks. We have to give a little bit credit also to the evolution of computing, the evolution of high performance computing architectures, accelerators that you learned the last time. So you have seen the NVIDIA curve of, advancing from Pascal, Volta, Ampere, up to Grace Hopper chips and Blackwell and so on. And this will not stop, right? We have the AMD Instinct cards giving competition from Cray. So there will be more and more coming. Hence, the fruitful results of deep learning is really interconnected with also what you see here, the training time, the footprint you have, right? If you have smaller problems, basically it's of course clear that the traditional models like random forest, SVM, statistical computing at large still can be done, right? Nobody says that deep learning will now rule everything. One of the key ingredients of deep learning is basically deep and, big data sets. Now, this leads to a domain called synthetic data sets. So people are thinking about, okay, if I don't swim in data, can I build data which looks similar? And there's also the overlap with high performance computing, again, a topic which I will not address much in the course, but of course you can use HPC simulations based on physics as an input to AI, right? And then you basically create maybe syntactic simulations where you enrich this with normal simulations, which might be not enough, right? Because the real world might be not giving you enough data, but you can create with maybe HPC simulations that are very similar to the real data. And then you basically learn better from it when you do again machine learning from it. So it's a sort of two-level, three-level way how you would use AI today. And it's a very complicated subject. Hence, we are in a point of time in history, I think, after my 20 years in HPC, where you say, we need complete professors on deep learning and HPC, or we need complete professors that, are teaching you not only in one course about deep learning, but teaching you the powers of transformers, teaching you the powers of encoding, embeddings, autoencoders. So we are in a time where deep learning is so large and has so many benefits. Leave alone in the middle of it maybe large language models, because we talk in the next lecture about it. So this is something that is not only having so much innovation, it's also giving you lots of impact to society. I mean, everybody of you is using ChatGPT probably more or less in one way or another. Everybody of you is using maybe the browser in Firefox that somehow can suddenly translate the whole web page into English, even if it's Chinese. So there are lots of impacts in life. And I think that's why it's also accredited that you see on the left side. And then I move to the next slide that, the pioneers of deep learning are rightfully credited to the so-called AM Turing Award. Some, basically, you probably know some of them, like Benjo, Hinton, and LeCun. And this is really important to understand that there is these godfathers in it, but they also derive some, credit from high performance computing, advances in GPUs, advances in the technology that may make it happen to compute deep learning today at scale. And that scale is really loaded, especially if you're extremely large deep learning networks, you have to definitively go across nodes. Leave NVLinks and what we learned the last time a bit behind, and really do distributed deep learning, things we will learn in lecture 7. So let's advance a bit, because many of you will now think, okay, we had this in the past. And also this slide was basically just a reminder of you about the differences, right? And it's important difference to understand now when we move ahead. So what we had in the last lecture part 1, was essentially this, right? We had this artificial neural network inputs, sometimes linearly using weight for one neuron. But of course, then suddenly when we add more and more neurons, we have this hidden layer. We have a whole bunch of neurons. And then we even a hidden, second hidden layer. And then an output layer, we come to the problem that actually the error cannot be, directly communicated back. Hence, we need back propagation of error through the hidden layers back in order to, let's say, add to the weight or remove some parts of the weights, the strength of the signal, in order to call it learning. This was also based on, gradients. So, I mean, basically we learned as an optimization technique, a minimum or a minimization for each of those. So hence computation expensive and so on. And with the feature engineering, what I did was, and showed you before, is basically in a one respect, we did a 1D vector. That was us, but we did this manually. So it's not that this neural network came up with it. So basically, that was our idea, to put features in a 1D model in order to make it learn in a perceptual learning model, or in a let's say, hidden layer neural network, which still captures the essence of one long vector as input. So that was sort of traditional machine learning. And then you can come on and go on and go on, and you can have some symmetries and numbers. It's an advanced topic, but you can do some so-called feature engineering, find better ways of crafting features. In fact, one of my early PhD students, who is in fact professor now, did actually the neighboring, with the so-called mathematical profiling techniques and trees to see how the neighborhood features would fit in the game. If you have, for instance, remote sensing data and land cover classification. So this feature engineering was traditionally a very big topic, how you prepare the data for the model. So deep learning changed this a little bit in something we called feature learning. So instead of saying you spend a lot of time manually, let the neural network think what is the best to learn. This is sort of a little bit misleading because we still have some hyperparameters to choose. So how big would a feature map be? How many convolutional layers I really have to learn features? How big should be, the subsampling be? How big should the feature map be? The filter I'm running over. So many terms that are not directly obvious to you. So it's something what will materialize hopefully in the next couple of lecture slides. But the point to get away is that now the deep learning networks are a little bit in a way to capture these features, right? And to digest more raw input. And with this, you can have some effects that you saw here on the pictures that, no matter what you put in, they still can, get the features of noses, ears, eyes, encoded, and then can much more easier recognize a person based on these features that they learned, instead of us saying, well, this is a nose, this is a eye, this is something. So in a way, this feature maps enables us to learn that on its own. So I will not play the video, you have seen that before, but you got also the message that the neurons we're talking about are so not really just deeper and deeper and deeper in a sense, they also have a sort of structure and an architecture, if you want, that is then this feature extraction layer. However, now that you had already part 1 and hopefully looked at this, you see the fully classified and the fully connected layer for classification here at the end features, again, often the softmax, right? The probability, again, of saying, well, we are still having 0 and 9, right? So there's a probability that this is an 8 or 9 because they're very close, looking very similar. But still, we have the softmax layer at the end for classification, fully connected. What changes a bit is the architecture that you have now in front in order to carve out features. And let's go a bit into this, how this is done more and more in the next couple of slides. So again, of course, using our example that we had of the basically handwritten characters that we want to identify. And always when I have this particular, let's say, examples here, it's also for you to understand that we have some of these numbers, maybe in the input data set that you see here, that is really not recognizable, right? So especially also for a human, right, that maybe should validate all of this. So you see here, I have no idea what that should be. Could be a 0, could be an 8, which is very small on the top and then very big on the bottom. Hence, there will be always some samples which are considered to be noisy. So that's the term in machine learning. Again, feel free to look on the machine learning course. Noise data means essentially we will learn from this, but we learn also not the best things out of it. So in other words, if we give this also a shot of classifying, and when let's say human don't even recognize this, how in the world should a machine do this? So in the other words, there will be never 100% performance, usually. If it is really like this, and it's either a toy problem, very well prepared, and basically having ideal setups like linear separability that we discussed with the flowers. That was also not true. I actually left out the third class, which was overlapping in this particular example. So the reality shows, again, would be not really happening. I just provided you with an idealized scenario. So in the end, there's a third class of flowers, which is another iris flavor of the actually making it much more difficult. And you see it here the same with the characters. So hence what we want to do, if you remember lecture, basically this lecture, but the first part, the end, we want to improve from 91%, okay, perceptron, 95% artificial neural network to layers. So what can we do better? But we also have to be realistic. And this is something which you see a little bit in this particular samples here. So probably no matter what we do, even with the power of deep learning, even with a full cluster of HPC and soon exascale, whatever, we will never achieve 100% performance, because the true error is in the data with this kind of samples, which are, really noisy, or in other words, not really recognizable, even if there is a label for it and should say, okay, this should be a 3, a 1 or something, but it doesn't look like me as a human for it. Hence, we have one interesting other part what I want to stimulate here. That is the so-called idea how humans work. Firstly, we said it's not recognizable for us. So what we do have in our brains, and more locally, if you want to see it also in our architecture of the eye, is a local receptive fields, right? So this idea is taken forward in the CNNs. And the idea is that we look usually when we identify a cow or a car or a cat, the famous examples of machine learning, which are not at all the essence, but it is something you all refer to. We're not identifying a cow by a pixel, right? We're identifying a cow by some certain pattern of colors over the whole animal. We identify a car by having wheels and maybe, some windows at a certain position or whatever. So hence there's a certain environment, region that you want to basically look at once in order to identify features like maybe car tire, or let's say a certain interesting color scheme on a cow, or whatever it is. Could be, of course, from a cat, some specialities, the famous examples. But we as humans do it like this, and you can see it as a sort of window of the whole scene that you look at. And that's exactly going with us now to the basic principles of why we have a convolutional network that is now doing, let's say, different neurons in different layers, and so to speak, redo the visual cortex, right? Maybe more or less the animal visual cortex, or not the human, which a bit more simpler, with different types of layers, convolutions, pooling, strongest single survive, for instance, max pooling, whatever, to see. And here's an example of 5x5 local connectivity. Looking at these 25 pixels at once give us much more indicator what happens. And it also directly, for those of you that looked intensively on part 1, gives you a hint what's now changing, right? We remember the vectorization and then the normalization. In a sense, we put everything in a very long vector. We don't do this now. We keep it at the pixels, but instead of using, let's say now the whole pixel at once, the whole image at once with 28 pixels, we have a so-called, a receptive field, and which is then realized by so-called windows, where you move over the neural network, which is a little bit explained here. And I will have also a couple of slides showing you how this works, of course, over time in the learning. And over time in the learning, this is now the point where also the convolutional, or basically the filter, comes in. So you look over the input space, you shift it, basically. We call that also a stride, which you can define. So how much the stride would be. Here in the example, we have a stride of 1. So we look at all of these different 25 pixels. We define the window size. We go over this picture systematically. And in the first next layer, hidden layer, we have a so-called feature map. What we have to define again in size, we say, okay, let's craft a 24 by 24 feature map. Again, something in the architecture that essentially you should choose as a human, right? So this is something also where the architectures, really differentiate each other from the type of application they are working on, from the data they have to digest. So here we assume a 24 feature map. And then with the stride of 1, we go through this and fill this next feature map, with some data. But with what data? And this is now the convolution principle, right? So basically, you have a so-called convolutional filter operation, or filter, basically, that you apply over it. And here's an example of it, I think quite nice, where you then get out the so-called convoluted feature. Here's an example where you have a 4x4, for instance, and this is completely done over this input space, if you want, at one step. And then we go to the next step of stripe 1, fill the next neuron, fill the next neuron, and you basically have this weights filling up with this convolutional operation then, and giving, let's say, the next layer some concrete number information, like the convolve features you see here. Here's a good filter, 3 by 3, so another example, but the animation shows clearly how that looks like. And with this, you basically have a more dense representation maybe of something that you identify in this particular layer. So obviously, this was so-called 2D, right? Now we have to think like real world data is different. In our remote sensing examples, we have even, really different data sets where we talk about hyperspectral or multispectral data sets where you have 200 dimensions in the data over land cover. And maybe, let's say, they are very overlapping in the dimensions, but still lots of data in different dimensions. Here's a 3D example standing largely for our AGB, something you can connect to. But it hasn't been so simple, in all the scientific and engineering examples. This is again more or less an idealized scenario with RGB, but it captures nicely the essence that there's different, let's say, dimensions now that you can put at once, right? We started with 1D with the array. Now we had then 2D, but now we can also think that data sets, like, for instance, as I said, with remote sensing has many, many dimensions. Bioinformatics stands also for very high dimensions, features of a person. And then, of course, here an RGB photo is just alluding to some very similar, but still trivial factor of go through. Still, what I can do is with a 3D aspect, I go through the data and fill the next feature map. And you can imagine with having more information and also the locality in, right? And this is a key term. We preserve the locality now in this convolutional neural networks, right? And many of the deep learning networks have similar tricks where they preserve some element in the input data. They encode it wisely, coming to embeddings, which enables us to do a decoding very simply. But they learned embeddings of the data, very dense representation, basically, of what we learn from data. Is another topic. I cannot talk much about it because we have a HPC course, not a machine learning course, but we publish a lot in this area. And this is also a cutting edge deep learning algorithm that basically should be taught in other machine learning courses and so on. So what you see also here nicely is it doesn't have to be one feature map, as you saw also in the previous convolutional neural network example. There were many different feature maps, and you define this, right? And the convolution filter you run over it might be different, right? And this is also another part. So hence, this is the first step that you learned already now in several examples, going from the input image to some feature maps. The same here with the convolution operation. And then you usually put it through a non-linearity, which might be after convolution a rectified linear unit or leaky ReLU or something. And the next step would be then to see, can we reduce the data, right? And this is a pooling step. So the pooling step then basically gives you different opportunities. You can pool from some certain space and using some particular function, very commonly uses max pooling in an analogy maybe of a little bit like the strongest signal survive, but there are many other options. And of course, this is now a systematic for this feature learning, which doesn't stop there, although it's indicating here a little bit on the picture. Now the power begins that you have this deep learning. So the feature learning just doesn't stop with one of these elements. You would go again and again and maybe create another convolutional layer afterwards, another convolutional layer, etc., etc. However, if you want to, let's say, classify a car that you see here, chances are that in the end, whatever you learned with all of these different layers, right? So convolution giving the idea of different, let's say, feature maps, and then you do the pooling, convolution, rectified linear, pooling, convolution, linear, etc., etc. At the end, for the classification, you would go to a dense network again. Now, this could be like 50 times, right? For instance, there's a residual network, ResNet 50, that I was alluding to in the last part of, basically in lecture 5, if you remember. So this has 50 deep learning networks doing similar things that we see here. But in the end, that's the interesting thing. We still have a flattening out, so a dense connection, so everything is connected to the out layer, where you then perform the softmax that you already know now, basically giving you the probability. Is this a van? Is this a cat? Is this whatever? But we all agree that it's probably a car, and we identified this car, and this is a little bit here in the picture, because there is some certain properties here, maybe the outer mirror or something that was identified as a features and so on, propagated through the layers. And then I can easily, let's say that this is a car. But many different features will probably have been activated going over the data set. Like I told you before, the car feature, right? Or basically the lights in front feature. And this would be activated when you do inference. So what we basically talked about a lot was learning. So we basically we train the whole network. We create these feature maps. We have this W's that you see also again here nicely in red, things we learn. So here we learn more or less a multidimensional matrix with these feature maps. But that doesn't matter. In the end, it's something we don't know, and the learning algorithms will learn it. But in the other end of the scale, you would say you learn something, okay, that's done. And then you have this learned network with the weights being settled, right? The weights are clear. Then you put a new picture in, a new car, and then basically based on this trained weights, the feature maps would fire. The network would fire in terms of features it finds also in newly unseen data, a car it never saw. Let's say you basically train a car with labeled data on BMW as an example, right? And you do this a lot of times and say, this is just a car. Chances are when you do this with proper data that you can give in a Jaguar or whatever else, a Mercedes, another car, could be Kia. Chances are because of the features of the car, it's very similar that it will still fire, of course, as a car, right? No matter what the brand is. And this captures also the essence of being well out of sample. In sample would be, okay, I would get the next BMW right. I trained on BMWs, that's okay. But what we want to achieve is that a deep learning network is smart enough to say, we want to be good out of sample. Any other car that comes. And, basically Mercedes is not far away from BMW all the time. Kias have also SUVs, for instance, and et cetera, et cetera, et cetera. So this captures nicely the idea of training and learning network, and then you perform inference on out of sample data and hopefully be right. And this is what we want to do in machine learning. Good. I think it captures all on the slides. I do something unusual for our, let's say, lecture here. I will break off quickly to some demo. Although it's not a practical lecture, but it's not a practical lecture in HPC. I wanted to allow me to give you this particular interesting website, which I found fascinating, and I think you should really try it out. And I do this since a long time in all my trainings to get students directly understand what we're talking about. And I think here is a good example. When I now craft our handcraft, element, many of you will see that's an 8, that's fine. And then, what is a little bit outblended is now exactly what we talked about, this window going over the data. They are all weights. This is all connected. So don't think about that this is now, something magic from one layer to another. So you see here, sometimes the connections are still highlighted to really make the connection for the different layers. But you also see that the 8 is so-called encoded in the next level as much more feature oriented. And then if you go down layer by layer with poolings and so on, you see just parts of the features quite nicely. And you see also the first guess here, it's basically the probability analysis, right? It's an 8, yeah, that's true. And the downsampled drawing sees almost like an 8, so this was simple. However, you see also from the probability perspective, as I told you, it's a softmax activation function somewhere here, right? And this shows you also that we go down, basically input convolution operation, creating a feature, some sort of rectified linear units or whatever activation function to capture nonlinearities to go to the pooling, next feature, and next, and next, and next. But the last bits is densely connected. Densely connected, again, stands for every neuron of one layer is connected to the other lump. You see this very nicely in this visualization, right? So I really want to credit here the authors. I think this is an enormous important part, not only in learning, also in research to understand really how it works. And you see here sort of the two dense layers connected, giving them the input to the softmax, which then gives you the learned probability from all of that before, right? This is all learned over time, iteratively, epoch by epoch, and batches by batches within each epoch. To come out to the solution, it's an 8. So obviously, we can also now think about more scenarios where it's not so easy, where you think, okay, it's a 6, but maybe it's this. And what you say, it's an 8, but of course, a second guess might be a 6 because I didn't connect this. When I connect it, then maybe if I redo it, it looks much more like an 8. Or like here, second guess is even a 1 because it's like very close to each other. So I think, long story short, play around with it, especially with these interesting things. 1 is a 1, 1 is a 1, but also you can write the run in a 1 that is maybe rather a 7, right? Depending on when I wrote it. So this is a tool I just wanted to bring you for an attention, and it's of course linked in my bibliography. So I will not spend much more time in it, but I think it captures nicely the essence. And if you go to the original page of this, let's say, brilliant author Harley here, you have different examples. You have also 1D, 2D, and I encourage you to play around if you really want to understand more on basically deep learning. However, we want to go ahead because the goal of my lecture is not to teach you completely deep learning, but also its interconnection with computing, right? So this is a key goal here. Deep learning you can learn essentially in the machine learning course, so in a deep learning course. Hence here we have to make the connection now to computing, and I think some of you probably already know what's happening, right? So in order to get all these different weights, we will learn. And you see here how we would define this. You see also much more elaborate code. We define now a 2D convolutional layer with input sizes. We have a certain kernel, basically size that we want to go over the data. And then when we have the kernel, we need to basically, with this convolution operation, ending up with a so-called activation function, and then having the pooling function to have sort of one layer really, if you want. And then we go to the next layer and the next and the next. So here you see one, let's say, convolutional neural network, which was, let's say, in the beginning of deep learning, really the modus operandi. Today, people would maybe rather go for, ResNet 50 or some residual network. But it captures still nicely the essence of this convolutional network, which shows you a dramatic increase in trainable parameters, right? And left alone that we actually left some things out here now, which are weight sharing and so on. So hence, when we do all of this with all this different convolution operation, feature maps, and again, pooling, convolution, and so on, we don't have any more 7,000 something, which we had in the perceptron. We don't have any more what we had in the artificial neural network world. We have now suddenly 1.2 million trainable parameters, right? So, and this is now something which of course shows you, okay, the more you do deep learning, the more computing needs to be done, the more optimization, the more weights. And this is now the footprint, right? So hence deep learning in one other view really required this computing power. Otherwise, you will spend hours on a CPU, right, doing this. Even if you have the power of shared memory, getting new data in, nicely read, you still have to do the computing. And it gives me also an opportunity to connect to the other part that we had basically in lecture 5, right? The other part in terms of, this vector multiplication, vector matrix multiplication, which are simple. Each of them, but very many of them, hence many core techniques, right? The instructions to update weights, to multiply it, right? As we have seen with the update rule really of the weights and so on, depending on the learning rate and stuff. So these are all in a way simple operations, but I do just very, very many of them, right? Depending on the input size of the graphics, the number of featuring maps, and so on. You see here 50 feature maps, right? So, and we have the connections, and all the connections are weights, and then plus the dense layers. So you see a little bit how it works here with the number of parameters, adding more and more. Each convolution operation has a very big input to play. Obviously, the dense one very much too, right? So this is in the end combining everything at the end. So has a big role to play in this rather simple network, right? We talk about not a ResNet 50 with 50 layers. This is like a so-called more or less 2 layers here, right? Where we have this and this layer, and then essentially in the end, you cannot really call it anymore, let's say a real layer, because this is again the usual, dense layer with a softmax to come to the number. That we also incorporate here essentially in the code. Let me just give you a couple of pointers also what has to be discussed. I mean, firstly, what you have seen is, I think if you put the input, we are not anymore doing this vectorization. I mean, this is by now, I think, pretty obvious. We just go with essentially this 28 by 28 input dimensions, and then we look at the data at once. We train still on normalized data. This is a little bit hidden here, right? So of course the grayscale is still there. So we don't want to have this with high numbers. Hence we actually normalize this here, so see dividing by 255. But essentially we look at this as a 3D problem, because then this also means we have to encode it in the 2D, what you have seen also here when we have this conv2D operation. So this is of course all fit together, and is also the idea now of thinking about what optimizer are using. These are now these interesting hyperparameters I'm alluding to at the end, more or less at the deep learning lecture, because we come back to hyperparameters later. Learning rate, optimizer, batch size, number of epochs, how long you learn. Many other parameters are the so-called hyperparameter that steer the learning process and also have an important role to play, as we will hear later. So in the end, when we do all of this and we'll compute this, you see in something what we sort of expected. So we landing somewhere, and I mean, here incorporated, what I forgot to mention is a bit of validation splits. Hence, we combat overfitting a bit, right? In other words, that's why we maybe not always have 100% in one respect, but we have seen in another respect, there are some samples we truly can never learn from. So we come to a more or less realistic setup of 0.99% when you have deep learning models. And, given the sheer data size and the, let's say, complexity of the problem at hand, this, network is already enough. No matter if you not put a ResNet 50 on it or so, you would never achieve 100%, right? And it would be probably even worse, because it would overfit. It has much more connections, much more weights to learn, but it has no data to learn from, because we have just 60,000 samples and 10,000 for test. This is not changing. And doing so and throwing then big, let's say, deep learning models on such a toy problem would basically also not help, because firstly, it would waste a lot of energy, right? So, I mean, it still would be trained on this data. And given the size of the whole network, and with 50 layers, you probably have lots of much more parameters, as you completely understand, hopefully by now, right? Instead of having this kind of 2 layers here, you have 50. So the parameters, which I think is best explained also in the large language models these days, right? If you know a little bit about your ChatGPT you here and there use, and the large language models, we talk about billions of parameters, not 1.2 million of trainable parameters, billions, right? And each of these have to be, learned, have to be, let's say, manipulated, have to be computed, and with other words, using energy of a CPU, of a GPU, together with many others. But long story short, I wanted to just make you sensitive to the point that, of course, a model we call that capacity or learning capacity of a model that you have in AI should match the problem at hand. In other words, you basically otherwise will definitively overfit or underfit, right? I mean, you can also see that a simple statistical method here would have maybe no chance. The linear learning models stopped at 90% performance, so here we have quite an improvement to go to this 2D setup and the nonlinearity and deep learning. So there are benefits. And if you have a more, let's say, complex problem like remote sensing, I said to you, with different pixels you want to analyze and so on, chances are you really have massive improvements with deep learning and can go nowhere with the simple learning models we started from, with the perceptron learning model, for instance. Again, when you try that out yourself, basically think about the right environment. Here you have a Jupyter notebook, things we already introduced a little bit in the course before, right? So this is something where the right packages have to be included, like Keras TensorFlow here. Sometimes you use maybe PyTorch, and it's important that the environment in this Jupyter notebooks also has basically a kind of kernel that is having these Python packages installed. Like, for instance, the Google Collaboratory. So if you want to play around a little bit with this example, so this would be a good example to use. Of course, we have also our HPC resources where you can use it. But with one GPU usage for such toy problems, it's still, let's say, an interesting environment. In HPC, we are much more interested in going cross nodes, really big setups, something I will also teach you in lecture 7, when we come then to distributed deep learning, as it is called, distributed training, if you're really precise on deep learning, because the inference is often very quick, right? As I will also explain you a little bit more in lecture 7. So overfitting, underfitting, and regularization, validation are all more, let's say, advanced topics. That's why I want to give you this video a little bit to look a little bit again why we combat overfitting in machine learning to have a much more realistic saying and realistic learning reporting, really, to who we report, whoever it is, your bank, as I said, or Netflix, where you create a machine learning system for. They want to have real values, and you should not basically either, in large language models, we would say hallucinate, but here we would say we would overfit and report a 99% performance, but maybe with regularization and validation and proper model selection, you come up to a performance of 80%. Now, when you report to your bosses at the banks, Netflix, that you can do every machine learning task at 99% on this data on the movies, then they will say, okay, you get a good check. But if they in their production every day in the bank and then in Netflix or whatever it is, right? I'm not paid by them. I'm just saying these are examples. Then if they see the truth is it's not 90, it's 80%. So then they want to quickly maybe their money back. Hence, it's important to have training sets, validation sets, test sets. It's important to have regularization, validation techniques. So I urge you again, not potter off with this course here today and basically the last one and the one we have next to just be a machine learning expert. You require some more understanding of statistical learning theory to really make that happen. However, I think it captures the essence in this lecture and also in the next one, why we need high performance computing. Today, it was more about the trainable parameters, the need for computing, more optimization of weights. So the next lecture will then capture the essence of why we go distributed, right? So why we don't stop with one node, but want to have many nodes for speed up and so on. So I stop here and we see us basically then next time with lecture 7 in distributed deep learning. Talk to you then.